So what we're going to look at today is we're going to be looking at homogeneous DEs with constant coefficients. These kind of differential equations come up quite often when we do applications problems. Say, for example, we'll see spring mass systems. We'll also see circuits. And those systems are going to be represented by these homogeneous DEs with the constant coefficients. Plus, sometimes they'll have them in forms of non-homogeneous forms. Where these are also going to become crucial is inside of, they're going to be essentially the first step in solving non-homogeneous differential equations. Because if you remember from our previous conversation, what we had to do was, in order to find the solution to a non-homogeneous differential equation, we'd add a complementary solution plus our particular solution, okay? And so what these are is they're going to be the solutions to our complementary part, okay? So what we have now is we have a set of differential equations, y sub n plus a1 y sub n minus 1 plus a2 y sub n minus 2 plus, and then go all the way down to a sub n minus 1 y, and that'll be set equal to 0. And then a1 through an of minus 1 are all going to be constants. So that's a requirement for us, okay? And we just want to represent that these are going to end up being our YCs. So they're going to be the solutions to their own systems, but at the same time, they're also going to be a part of the work when we actually solve non-homogeneous differential equations, okay? So given that that's the case, let's set forward the theory a little bit. So I'm going to go in now and I'm going to set forward the theory, the general theory for these homogeneous DEs with constant coefficients. I'm going to use like a generalized form, but then pretty soon afterwards, we're going to go in and we're going to do some examples. And I think sometimes the examples might be a little bit easier to follow. But this is for those people who, you know, they kind of want to see the overall, you know, method given any constants, okay? So we've got a differential equation of the form, we got y sub n minus 1 plus a1 y sub n, y sub n plus a1 y sub n minus 1 plus a2 y sub n minus 2 plus dot 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 plus a sub n minus 1 y equals 0. That's our form. And what we're going to do is we're going to posit that the solutions are of the form y equals e to the rx. And we saw that actually inside of the last lecture. Now what we're going to do is we're going to formalize the process. Okay? So we're going to say that the solutions are the form y equals e to the rx. One of the cool things about higher order differential equations is that this kind of thing where we're saying, okay, this is the kind of DE that I have. All right, and I'm going to suggest that this is what the solutions look like. That's how this kind of stuff works. We're like, oh, it's got this kind of solution, and then this is how we find the particulars of, say, for example, in this case, R. Okay, so we want to find R. That's our job. We're going to go out and we want to find R. And so I want to imagine what happens here. So this is the nth derivative of, in this case, e to the rx. Okay, and so we've got all these different derivatives, and so let's look at what happens. We start out with our function y equals e to the rx. So y prime is going to end up equaling re to the rx. Y double prime will end up being r squared e to the rx. We're just taking a derivative each time. Y cubed, or y triple prime equals r cubed e to the rx. Y quadruple prime is going to equal r to the fourth e to the rx. So what I think you want to get is like, this is just going to happen until we get down, dot, 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 right? Y sub n is just going to be r to the n e to the rx. Choose an r, go see that that's the case, but that's exactly what's going to happen. Every time I take the derivative of e to the rx, I've got to multiply it by another power of r. So what I'm going to do is I'm going to plug these in because they are the suggested solutions. I'm going to plug them into my differential equation. So here's my dE. And so now y sub n is now r to the n e to the rx plus a1 r sub n minus 1 e to the rx plus a2 r to the n minus 2 e to the rx plus dot 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 plus a sub n minus 1 a sub n minus 1 e to the rx equals 0. Now notice each term on the left hand side is going to have this e to the rx in there. Okay? So we can actually factor it out. We're going to end up with e to the rx times, and then this is going to be r to the nth power, and this is now powers. These are actually powers. They're not actually derivatives any longer. Plus a1 r to the n minus 1 plus a2 r to the n minus 2 plus, and then dot, 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 a sub n minus 1 equals 0. E to the rx cannot equal 0. It never does, right? Okay, e to any power is never going to equal 0. So what that means for us is that means that r to the n plus a1 r to the n minus 1 plus a2 r to the n minus 2 plus dot, 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 a to the n minus 1 has to equal 0. Okay, it has to equal 0. And so consequently, what we want to do here is we want to solve this polynomial for r. And we can either factor it or for r. We can either factor it, we can use some technology in order to solve the polynomial. Okay, but we want to solve the polynomial for r. And once we solve the polynomial for r, it gives me my solution. And here's the idea, okay? First things first, I want to actually give this a name. This polynomial, what we're going to call p of r, is r to the n plus a1 r to the n minus 1 plus a2 r to the n minus 2 plus, and then we just keep going until we get to a to the n minus 1. And that's called the auxiliary polynomial. Okay, so that's our auxiliary polynomial. And the equation r to the n, a1 r to the n minus 1 plus, and then go all the way down to a to the n minus 1. So it's that polynomial instead equal to 0, the one that we're solving, is called the auxiliary equation. Okay? And so what we have here then is we have the auxiliary equation. The solutions to the auxiliary equation are going to be, we'll call them R1, R2, all the way down to R sub n, because the power of R is the nth power, right? It's an nth power polynomial, so we're going to have R sub 1 through R sub n, and this is accounting for repetition and complex roots. So accounting for repetition and complex roots, and we'll talk about that in a little bit more in a bit. And so our solutions will then end up being of the form y equals e to the r1x, y2 equals e to the r2x, y3 equals e to the r3x, dot, 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 all the way down to yn equals e to the rnx. Okay, now they might be repeated roots, and we'll talk about them. They actually change up a little bit. They might also be complex, because a polynomial could possibly have complex solutions, and we'll look at what those look like as well. But pretty much, right, basically, and this is not entirely the case, they're basically going to be of this form. Okay, and those are going to end up being our solutions. So essentially what we're going to be doing is we're going to be taking our differential equation, we're going to be adapting it, transforming it into a polynomial, solving for the roots of the polynomial, and then those roots in the form of e to the rx end up being the solutions to our differential equation. So let's go find the general solution to y double prime minus 3y prime minus 10 equals 0. So what we're going to do here is we're going to actually rewrite this as a differential operator. So this differential operator is going to end up being d squared minus 3d, d squared y minus 3dy minus 10y equals 0. Okay? And the reason why we're going to do this is because just inside of the method, this differential operator, what we can do is we can kind of pull it away and look at just like the linear aspects to it. And then we'll turn that directly into our polynomial, into our auxiliary equation. So we're going to pull this out. So L is going to be then d squared minus 3d minus 10. Okay? And we call this P of d. Right? Just for our purposes, it's called the polynomial differential operator. It's going to be P of d. We're going to replace that with r, and we get P of r equals r squared minus 3r minus 10. Okay? And you'll notice that that's your auxiliary polynomial. Now we're going to set that equal to 0. R squared minus 3r minus 10 equals 0. And that gives me r minus 5 times r plus 2 equals 0. So r1 will equal 5, and r2 equals negative 2, just as we solved the polynomial. So my solutions are y1 equals e to the 5x, and y2 equals e to the negative 2x. And we write that together as a single value. Y is going to equal then ce to the 5x plus, or c1e to the 5x, because we have two constants, plus c2e to the negative 2x. And that is the general solution to the differential equation. All right, so we want to find the general solution now to d minus 2, d minus 3, d plus 4y. Now, from the perspective of the differential operator, what we're doing here is we're taking like the derivative each and every time. So what we have here is we eventually have like a third derivative. And if we're working with differential equations that have constant coefficients, homogeneous differential equations with constant coefficients, then actually we can do this kind of like factoring. It's not really factoring, but it turns out that we can put the derivatives in any order that we want to, okay? And we can also like kind of break apart our differential operators in this particular way, and it basically looks like factoring, even though that's not exactly what it is that we're doing. And so I want to be careful about that. We talked about that a little bit inside of the last chapter, but we got to, you know, in this case, because we're looking at constant coefficients on our differential equations, we can do this, okay? So what I'm going to get then is I'm going to get P of D, that polynomial differential operator, is just going to actually be just this. I'm going to write it straight down. D minus 2, D minus 3, D plus 4. And then I can change that to P of R. I replace my D's with R's, and that becomes R minus 2 times R minus 3 times R minus 4, or R plus 4. Okay, and that's our auxiliary equation. And then we have R minus 2 times R minus 3 times R plus 4 equal to 0. Solve that now, and it's fully factored, so it's really not all that, we can factor it really easily. So solve that, and we get R equals 2. We'll have R1 equals 2, R2 equals 3, and R3 equals negative 4. So my solution is going to be Y equals, and we'll write it as C1e to the 2x plus C2e to the 3x plus C3e to the negative 4x. And that's the solution to the differential equation. All right, so in this case, when it's in this form, it's really quite simple to see what your solution actually is. Now, notice here, and this is going to be our first piece here, is that P of R has unique real roots. So that's an important piece here, that we have unique real roots to P of R. And since P of R has unique real roots, this works very straightforward. We're going to have two other situations. The second situation is when we have repeated roots, and we're going to see what happens then. Okay? And the third situation is when we have complex roots, and we're going to have to deal with the complex roots as well. Okay? So when we have repeated roots, when we have complex roots, and we have unique real roots, those are the three situations that we have. We've just seen unique real roots. Let's take a look at repeated roots. Now let's look at a problem in which what we're dealing with is we're dealing with a differential equation where the auxiliary equation or the auxiliary polynomial has multiple repeated roots. So let's say, for example, I have y triple prime minus 18 y double prime plus 108 y prime minus 216y. What we're going to get here when we rewrite this as a differential operator, this is going to be d cubed minus 18d squared plus 108d minus 216y equals 0. And we're now going to actually rewrite that as the auxiliary equation, right? We'll just take this. P of d is just going to be d cubed minus 18d squared plus 108d minus 216. And we're going to get r cubed minus 18r squared plus 108r minus 216 equals 0. When we factor that, we're going to get r minus 6 cubed is equal to 0. So what we now have is we have a repeated root. So we've got r1 equals 6, but it's got a multiplicity of 3. Okay? So multiplicity equal to 3. So consequently, we're not going to have, it doesn't make sense for us to have e to the 6x 3 times. Okay? It doesn't make sense to have e to the 6x 3 times. We can have one of them. We'll have like y1 equals c1 e to the 6x. But we're going to need linearly independent solutions. Okay? So remember when we talked about the general theory, we started out with the fact that we're going to need, right? We're going to need, in this case, we're going to need 3 solutions because the order of this this differential equation is of order 3. So we need 3 solutions, but they all need to be linearly independent. If I pick up e to the 6x, it's not going to be linearly independent with itself. That doesn't make any sense. So what we need to do is we need to modify it. And that's what we're going to do right here. And our modification now is to say, okay, y2 is going to equal, and it'll be c2. We're going to have some unknown constant, and I'm just going to add a power of x. In this case, x to the 1, and it's going to be x e to the 6x. Okay, so there's my modification. And then I'm going to have y3, and we're going to need that y3 is linearly independent from y1 and y2. So that means we're just going to take c3, my constant, and have it be x squared e to the 6x. You can go in and use the Wronskian, and if we use the Wronskian, you'll see that these 3 solutions, they're going to be linearly independent. And because what we're looking at is we're looking at, the third derivative, the x's go away, right? When we actually, they end up getting subtracted out, and we end up with the solutions to this differential equation, despite the fact that they've got x's in them and not just e to some power, okay? So we're going to get y equals c1 e to the 6x plus c2 x e to the 6x plus c3 x squared e to the 6x, and that's going to be our solution. So the way to modify for repeated roots, okay, say for example, we've got a multiplicity, we'll call it the multiplicity equal to n, all right, and the root r equal to r1, then our modification is going to look like this. y1 is going to equal e to the r1x, so that's the first one. y2 is going to equal then x e to the r1x plus, or excuse me, then we'll go y3 is going to equal x squared, right? So we're just going to add in a power of x e to the r1x, keep the root, all the way until we get yn is going to equal x to the n minus 1 e to the r1x. Okay, so just add an x each and every time for as many solutions as you need based upon the multiplicity of the root. Okay, and that's actually how we deal with repeated roots. So let's take a look at another example of our repeated roots. Now we've actually got this. We've got our polynomial differential operator actually factored. So what we can do is we can rewrite this as r minus 1 to the 4th times r plus 3 squared equal to 0. And that's our auxiliary equation. So we're going to get r equal to 1. It's going to have a multiplicity, call it m1 equal to 4. And we're going to have r2 equal to negative 3. And we're going to have an m2, its multiplicity end up being equal to 2. Okay? So we're going to actually have 2 sets of repeated roots in this case. We'll notice now we've got the ones for 4, so we're going to get y equals, and I'm going to write this all out as a single solution, c1 e to the x, right, because it's e to the 1x, plus c2 x e to the x, plus c3 e x squared e to the x, plus c4 x cubed e to the x. And notice now I've got 4 solutions with that particular root, the e to the x root. Now I'm going to do the ones for negative 3, the root negative 3. So this is going to be plus, and this will be c5, okay? c5, and it'll just be e to the negative 3x. So we don't actually like add in a power of x because we've now changed roots. We've now got a different root, so we don't actually need to use a power of x. We can now just use the linearly independent solution. plus now c6 x e to the negative 3x, because I need 2 repeated roots for negative 3x. Okay, so what we see now is we see every time we change our root, right, we start over in terms of the powers of x. Okay, and that's essentially what we do, and that's how we deal with repeated roots when we're solving these kind of constant coefficient problems. Let's suppose that we want to find the general solution to y double prime plus 8y prime plus 20 equals 0. And so now we're going to look at the situation in which we have complex roots. Okay, so if I rewrite this as a polynomial differential operator, I get d squared minus plus 8d plus 20y equals 0. And so then r squared plus 8r plus 20 equals 0 is my auxiliary equation. Using the quadratic formula, I get r equals negative 8 plus or minus the square root of 8 squared minus 4 times 20 times 1 all over 2 divided by 1. This ends up equaling negative 8 plus or minus the square root, and this is going to be 64 minus 80, so that's going to be negative 16 over 2. And so we're left with negative 8 plus or minus 4i over 2, which ends up being negative 4 plus or minus 2i as the solution to our auxiliary equation. So now we've got this solution. So if I wrote it as y equals e to the negative 4 plus or minus 2i x, right? That's the form of our solutions normally. Well, what we're going to need to do is we're going to need to actually modify that, because that doesn't really help us out a ton. I mean, it does and it doesn't. What we're going to use is we're going to use something called Euler's equation. And Euler's equation looks like this. Okay? We're going to get that e to the a plus bi. And it turns out we're only going to need one of those solutions. We're not going to need the plus or minus. We're just going to need one of them. Is going to equal e to the ax. Okay, so the a is the real part times cosine bx plus I sine bx. And you may remember that. You might have done that in your pre-calculus class, something along those lines. But that's good. That's Euler's equation. And what we'll do then is we'll turn this into two solutions. It's going to end up being c1e to the ax cosine bx plus, and we're going to drop off the I. And the reason why we can drop off the I is because if you remember, any linear combination of these solutions is going to be also a solution. So if basically I just multiply by I, or it's not really multiplying by I, you actually end up subtracting out the sign values, we can drop the I and end up with a real valued solution, which is what we want. We don't want the complex one, we want the real one. So we're going to drop out the I goes away, and we're left with c2 e to the ax sine bx. And those are actually the two solutions that we'll get if we actually have something of e to something of the form e to the a plus bix. Okay, so e to the a plus bix is going to end up giving me c1 e to the ax cosine bx plus c2 e to the ax sine bx. So now let's go over here to my equation, the one that I was using before. So this is going to end up being c1 e to the negative 4x cosine 2x plus c2 e to the negative 4x sine 2x. Okay, so all we need to do, the real part becomes the power for e, and the imaginary part becomes the coefficient in front of our x inside of the argument for cosine and sine. And those are our solutions. And so that's the solution to our differential equation. Let's take a look at another example. All right, let's look at another example with complex roots. And we want to solve the d squared plus 9y equals 0. So I've got my auxiliary equation is going to become r squared plus 9 equals 0. And so we get r equals plus or minus 3i in this case when we solve. Now, you'll notice that this is going to end up being e And there's no real part, so we could rewrite this as e to the 0 plus 3i. Okay? And so if I rewrite this, and you don't actually have to write the 0i plus x, you don't actually have to write the e to the 0th power. I'm just doing this in order to kind of show it. This is going to end up equaling, okay, if we rewrite it, e to the 0x cosine 3x plus e to the 0x sine 3x. Okay? So e to the 0x, that's just 1. So this is going to end up just being equal to cosine 3x plus sine 3x. We'll put on our constants. We're going to get c1 cosine 3x plus c2 sine 3x. And that is the solution. All right? Since this only has an imaginary part, we're not actually going to have an e to any power. That's going to end up just being 1. It's e to the 0th power. And then we're just going to need the argument instead of the sine and the cosine to be the 3. So let's solve the dE. We got d minus 2 squared times d squared plus 6d plus 12 squared. And then d minus 1y equals 0. And now what we've got now is we've got mixed roots. We're going to have repeated roots. We'll have complex roots. And we will also have some unique roots. So first, we've got d minus 2 squared. Okay? Let's rewrite this as our auxiliary equation. So r minus 2 squared times r squared plus 6r plus 12 squared times r minus 1 y equal to 0. So if I look here, I'm going to have r minus 2 squared. So that's going to be, we'll let r1 equal 2, and it's got a multiplicity of 2. We'll have the r minus 1, so we've got r minus 1. That's going to give me r2 equal to 1. We'll let that be that way. And then we're going to have r squared plus 6r plus 12. And that's going to actually be squared. So let's first find the root. So we're going to have r squared plus 6r plus 12 equal to 0. So r is going to equal negative 6 plus or minus the square root of 6 squared minus 4 times 12 divided by 2 times 1. So this ends up being negative 6 plus or minus, and this is going to end up being square root of negative 12 over 2, okay, which equals negative 6 plus or minus 2i root 3 over 2, which is negative 3 plus or minus I root 3, okay? And that actually has a multiplicity of 2. So we'll call that M3 has a multiplicity of 2. So now we're going to use these. We're going to actually break out all of our different techniques here. So we'll first start out with our repeated roots for R2. So y is going to equal C1 e to the 2x plus C2x e to the 2x because we have the repeated root. Plus, and then we'll have R2 equal to 1. That's just going to be C3 e to the x. Plus, now we're going to have C4. Okay, C4. And we're going to notice that the real part is negative 3. Okay, so it's going to be C4 e to the negative 3x cosine root 3x plus C5 e to the negative 3x sine root 3x. And notice though we have a multiplicity of 2. So what we're going to do in order to deal with that multiplicity of 2 for our complex roots is we're just going to multiply by a power of x. So this is going to end up being plus C6 x e to the negative 3x sine root 3x plus C7 x e to the negative 3x cosine root 3x. So we deal with repeated complex roots the same way we deal with repeated real roots, by just going in here and, in fact, multiplying by a power of x for each repetition. I wanted to actually add in a note, and that note has to do with how many, notice how many solutions that we have here. And this is just a good way to make sure that you know that you've got enough, okay? So if we look here, I've got 7 different solutions. Okay, 7 different solutions. We write them all as a linear combination. If I go up to my differential operator, you're going to see I've got a squared term, so that's 2. Okay, and then I've got a squared term, but then it's going to be squared. Squared, squared, so that's the fourth power. So that's 2 plus 4, that's 6. And then I've got my 1 for d minus 1, so that's 7. And that's also how I know that I'm going to end up with 7 different solutions or linearly independent solutions to this particular homogeneous differential equation. It's just something to kind of keep in mind. Well, I'll point it out every once in a while as we're working, is like how many of these solutions should I expect to have? So just to summarize, to solve a homogeneous differential equation with constant coefficients, we're going to rewrite the differential equation as a polynomial differential operator. Then we're going to substitute Rn for d and construct the auxiliary equation. Then we'll solve the auxiliary equation, and the solutions to the auxiliary equation are the solutions to the dE in the form y equals e to the Rx. So those solutions, y equals e to the Rx, we've got to have 3 different kinds of roots, right? And they have 3 different ways of interpreting the roots of solutions, and we showed some examples, and we actually went through that whole process. We either have unique real roots, we have repeated real roots, or we'll have complex roots. And those are actually our options in terms of dealing with the solutions to these homogeneous differential equations. So that completes the lecture.